In this video, we continue with chapter 5.1, examples and concepts. We are going to continue to discuss the dot product and look at the properties of the dot product in theorem 5.3. So if u, v, and w are vectors in Rn and c is a scalar, then the properties listed below are true. We saw in the previous video that we know we can multiply in any order. Multiplication is commutative in the real numbers. And so u dot v is equal to v dot u, our first property. We're going to prove that down here. Our second property is distribution. So u dot v plus w, well, that u dot product distributes through to give us u dot v plus u dot w. A scalar multiplication can be distributed to either u or v. So if we've got c multiplied by the dot product of u dot v, then we get the same result if we multiply the scalar first by c and then dot it with v, or if we multiply the scalar by c and then calculate u dot v, or u dot cv in that case. The dot product of a vector with itself, we say, is the square of the norm or the length of that vector. So you can think about it as just the v1 squared plus v2 squared all the way through adding vn squared without the square root, because we're squaring the norm, if that makes some sense. And then the dot product of the vector with itself is, of course, greater than or equal to 0. And the only way that we're going to get a 0 there is if and only if the vector v is the 0 vector itself. Otherwise, when we square each of these components of v and add them up, we're going to get a positive value. So let's take a look down here at the proof of that first property, the commutativity of the dot product. So the proofs of these properties all follow from the definition of the dot product. We're going to prove the first two in this video, and then you could use the definition to prove properties 3, 4, and 5. So for example, for the first property, you start with u dot v, and then following the definition of the dot product, you've got u1 multiplied by v1 plus u2 multiplied by v2 all the way through plus un multiplied by vn. But we know that multiplication is commutative, so in the second row here, we are just reversing the order of our multiplication here in the real numbers. So we can rewrite this as v1 u1 plus v2 u2 component-wise all the way up to plus vn un, which is just the definition of v dot u. So you can see how you could do something really similar with v dot v to have v1 dot v1 plus v2 multiplied by v2 all the way through vn by vn, and then you get what we've got up here, and then that's just a definition of the norm squared. So you can see how property 4 would be proof similar. Let's look at the proof for property 2, the distribution property here. So if we expand out u dotted with v plus w, that's all these elements u1 through un of u dotted with the elements of v plus the elements of w. So if we add up the elements of v plus the elements of w, component-wise, we've got v1 plus w1, v2 plus w2, all the way through vn plus wn. And now we want to dot u with that. So u is just component-wise multiplied by each of those additions, each of those sums of v1 plus w1 through vn plus wn. And then we know from real number properties that u distributes through with multiplication. So then we've got u1 v1 plus u1 w1. And then the next component is u2 v2 plus u2 w2. And then we can just split these up and have u1 v1, u2 v2, all the way through un vn plus u1 w1, u2 w2, all the way through un wn. And then we can separate that back out into the dot products so that we end up showing that this is equal to u dot v plus u dot w. So again, in this proof, we're just following the definition of the dot product. So the remaining properties you can prove using the definition of the dot product. All right, so Rn combined with these usual operations of vector addition, scalar multiplication, vector length, and the dot product together forms what's known as Euclidean end space. And then here's a little optional aside for fun. Non-Euclidean spaces So most everything we're used to thinking about is a Euclidean space, and what we're going to talk about in this class is Euclidean space. But non-Euclidean spaces come from physics, and they include elliptic space, which is curved, and so you can't smoothly map the curve to Rn because of the curvature, and it has a different definition of distance. Imagine trying to think about distance on a circle versus distance in a grid. It would be different definitions there. Hyperbolic space, which is curved and has a different definition of distance. And then Minkowski space, which I've included a diagram of down here. So Minkowski space is used in Einstein's special relativity. So if you continue to take math and physics classes, you can have some fun and do some calculations in special relativity using Minkowski space and differential geometry. And so that replaces the non-negative dot product with an interval that can be negative. And so that comes up in Einstein's special relativity theories. So here's our usual three-dimensional Euclidean space on the left. And then you can see Minkowski space has the observer at the center, and there's a future light cone and a past light cone when we're thinking about special relativity. So that's beyond the scope of our class, but really fun to read about. So you can go read on Wikipedia online about Minkowski space, or take a physics class down the line. Okay, let's look at this example. In our example, we're going to find u dot v, v dot v, the norm of u squared, u dot v multiplied by v, and u dot 5v. And we're going to do all this for u is 2, negative 2, 1, and v is 2, negative 1, and 6 here. So u dot v is just the component-wise multiplications added up, so we get a 0 there. V dot v is just each component of v multiplied by itself, 2 times 2, plus negative 1 times negative 1, plus negative 6 times negative 6. So that tallies up to 41. The norm of u squared, well, that's just u dot u, back from our definitions in the properties of the dot product that we saw back in Theorem 5.3. So you can say, oh, that's just component-wise 2 times 2, negative 2 times negative 2, and 1 times 1. So that tallies up to 9. And then u dot v multiplied by v, well, we know from A here that u dot v is 0. So when we multiply through, that just zeroes out everything in v, so we get 0 there. And then u dot 5v, we know from our property 3 that we can move that scalar out front. So we can say, well, that's just 5 multiplied through by u dot v. So it's 5 times 0, or 0. Okay, let's take a look at Theorem 5.4. This is the Cauchy-Schwarz Inequality. So if u and v are vectors in Rn, then the absolute value of u dot v is always going to be less than or equal to the norm of u multiplied by the norm of v. And you can think about the norm of u and the norm of v as the length of u and the length of v. So let's start with case 1, the simple case if u is 0. So if u is 0, then it follows, well, u dot v is 0, dot v is 0. And then the norm of u is also 0. So 0 multiplied by the norm of v is going to zero everything out. So in the most simple case, when u is 0, the theorem is true. And then you could say, by symmetry, if v is 0, same results. So now we're going to assume that u is not 0. So we're going to let t be any real number, and then consider the vector t multiplied by u plus v. So t is our scalar multiplication here. So then the product, if we do t u plus v dotted with t u plus v, that's going to be non-negative, we know, because you always get non-negative, greater than or equal to 0 values for dot product. So then it follows that this is going to be, if we expand out, t squared, because we can pull that scalar t out of both terms, multiplied by u dot u plus 2tu multiplied by u dot v plus v dot v. And so that's going to be greater than or equal to 0. So now we're going to let a equal u dot u, and b is going to be 2u dot v, and c is going to be v dot v. So that's going to give us a quadratic here. We're going to have this at squared plus bt plus c. And this is a quadratic that's going to be greater than or equal to 0. So the quadratic's never negative, so it has no real roots, or it has a single repeated real root down there at the 0. So now let's think about the quadratic formula. So by the quadratic formula, this implies that the discriminant b squared minus 4ac is less than or equal to 0. Okay, so then our b squared minus 4ac is less than or equal to 0. By some rearranging, we move 4ac over to the other side. So we get b squared is less than or equal to 4ac. And now we're going to plug back in our substitutions here. So b was 2 times u dot v. So b squared is going to be 4 times u dot v squared. And then 4ac, a was u dot u, and c was v dot v. Well, those are just the norms here of u and v. So that's saying 4 u dot v squared is less than or equal to 4 of the norm of u multiplied by the norm of v. I hope you see where we're going with this. Divide through by the 4s, and we get u dot v squared is less than or equal to, oh, sorry, this is the square root of the norms here. So then u dot v squared is less than or equal to u dot u multiplied by v dot v. And so then we take the square roots, that's when we get our norms here. So this was actually the norm squared. Okay, so when we take our square roots, we end up with the norms. Okay, so let's verify the Cauchy-Schwarz inequality for the vectors u equals 1, 1, negative 2, and v equals 1, negative 3, and negative 2. So u dot v is going to be 1 and 1 makes a 1 here, plus 1 times negative 3, plus negative 2 times negative 2. So that adds up to be a 2. And then the norm of u is the root of the 1 plus a 1 plus a 4, so root 6. And the norm of v is the root of 1 plus, that'll be a 9, plus a 4, so that's root of 14. So then u dot v in absolute value, that's just a 2. And the norm of u times the norm of v, that's 2 times root 21 if we simplify. So it's about 9. So this is definitely true. 2 is less than 9. So you could pick any vectors and go through the calculations and verify here. Okay, so what Cauchy-Schwarz gives us is that definition for the angle theta between two non-zero vectors that we saw in our 2 holds. We can extend that to Rn, n dimensions. So in general, our same formula holds in n dimensions that cosine theta equals u dot v divided by the norm of u multiplied by the norm of v. And that holds for angles between 0 and pi. And there's an important remark here to note that the angle between the 0 vector and another vector is not defined. So this only holds for non-zero vectors. All right, let's take a look at 2 examples, finding the angles between 2 vectors. So in our first example here, I'm gonna let vector u be cosine of pi over 6 and sine pi over 6 in 2D. And vector v is gonna be cosine of 3 pi over 4 and sine of 3 pi over 4. So following our formula here that we got as a result of Cauchy-Schwarz inequality, the cosine of the angle theta between u and v is given by u dot v divided by the norm of u and the norm of v. So here's our calculations in the next row. So when we do u dot v, we're going to get the cosine pi over 6 from the first component of u multiplied by the cosine of 3 pi over 4 from the first component of v. You can think about these as u1 v1 plus the first component or the second component of u, so u2 multiplied by v2, sine of pi over 6 multiplied by sine of 3 pi over 4. And then this all gets divided by the norm of each. So the norm of u is the square of cosine of pi over 6 plus the square of sine of pi over 6. And we know from Pythagoras, this is just gonna all be 1. And then similarly, the cosine squared of 3 pi over 4 plus sine squared of 3 pi over 4 is also going to be 1. So we're going to get 1 in the denominator, and then the numerator, this is going to simplify to be cosine of pi over 6 minus 3 pi over 4 using our trig properties. And so we can say, well, this is going to be cosine of negative 7 pi over 12 when you find your common denominator there and combine. And then using symmetry, we can say, well, this is just, since we have to be between 0 and pi for our angle, this is just a cosine of 7 pi over 12. So our angle theta here is 7 pi over 12, which radians, which is equivalent to 105 degrees. So it's important to remember that your angle theta has to be between 0 and pi. So if you're doing calculations like this where you end up outside that, you have to use your unit circle to figure out what is the corresponding angle between 0 and pi. And in this case, it's a coincidence that we just got to flip the sign. So you'll have to consult your unit circle and check. Okay, let's take a look at another example. So now we're going to use points in R3. So we're going to have U is 1, 1, 1, and V is 2, 1, negative 1. These are vectors, I should say, in R3 vectors, and these are the endpoints of the vectors. So the cosine of the angle is going to be the dot product divided by the norms. So the dot product with our component-wise multiplication is 1 times 2 plus 1 times 1 plus 1 times negative 1. So we get the 2 on top. And then in the denominator, the 1 squareds from u give us a root 3. And the root for v, let's see, that's going to be a 4 plus 1 plus 1, a root 6. So we've got down here root 3 times 6, or root 18. So that got simplified into a root 9 and a root 2. So that 3 down here comes from the root 9. And then we can rationalize this to get rid of the root 2 in the bottom. So that rationalizes out to this root 2 over 3 that we see as a final answer. And then theta is the arc cosine. So when we say cos inverse like this, remember that's just arc cosine. So depending on what kind of calculator you're using, the key might look like the cos with a negative 1 there, but that's not 1 over cosine. Be careful. It's what we think of as the arc cosine. Or your key might say arc cos, depending on if you're using Desmos or the TI calculator. And so that works out to be 1.080 radians. Or if you want to explain it in degrees, that's 61.87 degrees. But again, I am fine with you leaving it in the arc cos form. So you can say arc cos of root 2 over 3, and that's an exact answer. Okay, in the next video, we are going to look at what it means for vectors to be orthogonal.